Step, we have the spicy Dr. Jiannan from Snarkify. Please, everybody, a round of applause. I'm really looking forward to this one and all of the highly contested, hotly contested ideas you have.
Thank you.
Okay.
Thank you, everyone. So, do I look my deck here? Okay. I'm Jiannan Ouyang again, co-founder and CEO at Snarkify. Today I'm going to present about our end-to-end zkEVM proving with GPU acceleration. Okay, next slide. Cool. So first of all, what is Snarkify? I think most people know us because of our Z-Prize winnings. Like on my slide, I listed 6 first places we won over the past 6 years. In the most recent one, which is a GPU Planck end-to-end proving, we achieved 900 speed up over GPUs on a single device, which is even mind-blowing for myself when I first see the result. For our company, we actually have a vertical integrated solution on different of the tech layers of the stack. So we are building a decentralized proof network that provides end-to-end proving for zk rollups. By end-to-end, I mean we work on the bottom layer, which is GPU deeping, and the middle layer, which is a GPU acceleration library. And on the top of that, we also work on zk proof systems and zkEVM optimizations, so that the whole stack is vertically integrated and optimized together to achieve best performance, latency, and cost. Next slide, please. Oops. Okay, so what is our end-to-end proving? If you look at the top, those are our potential customers. In the previous panel, I mentioned that zk layer 2s, zk rollups are the main demand providers right now. So what do they have in common? If you look at native zk rollups, as well as the open source zk stacks, and the so-called OP zk rollups, actually all of them are generating block spaces that needs to be proved. Then you figure out what's the most efficient way to prove those block spaces. There are the traditional approach, which is you create a manually written circuit. For example, the zkEVM circuits from PSE and Scroll. They use Hello 2 to manually write a giant EVM circuit to prove the zkEVM. This is a proof system circuits I'm going to cover today. But the next generation solution is to use zkEVMs to prove Rust code, like Wrath or that from RISC-0. You have a RISC-V zkEVM, and you can prove all kind of Rust code. And in this case, you use it to prove a Rust Ethereum node. So beneath of the zk rollup layer at the top, we have a layer of zkEVMs. We are zkEVM agnostic. So our position is to pick the most performance and promising zkEVM architecture and do GPU integration with it to build GPU acceleration libraries for this particular zkEVM. And actually, those GPU code and the zkEVM is tightly coupled. So it's not like we just took some of the computer kernels, for example, NTT, and plug in a GPU NTT kernel to make it faster. That won't work. You have to look at the whole thing end to end. You measure where the bottleneck is, you rewrite many of the code, and as well as optimize for the workflow. For example, you figure how to lay out the data optimized on the different GPU devices so that you can have optimal data communication, etc. So the point is the GPU library and the zkEVM has to be tightly coupled and integrated together. Then at the bottom, we have the platform layer, which is a decentralized GPU supply that can provide you cost-efficient GPU supplies from those crypto miners where they have a lot of GPUs that are sitting idle. Okay, next slide. Okay, here's my agenda today. I'll do a case study of our integration with Scroll in production, like trying to showcase that. I tried to do a live demo here today. However, like the setup does not allow me to use a laptop. But you guys feel free to check it online. All those stuff are in production. You can see it on your own. You can check out our website and try. Then I'll explain how our architecture support the Scroll integration, and most importantly, what's the core component that's the in-house GPU prover we built. Right now, we are the only prover network that can provide both the GPU hardware and the in-house GPU prover, like end-to-end in-house. All the other GPU providers, prover networks are kind of running third-party provers from either zkSync or from Scroll, where they are just improving the GPU hardware. We do both GPU supply and software in-house. Okay, next slide, please. All right. First of all, our integration with Scroll. Okay, next slide. Okay, this is already live in production. It's called a demo, but I can't do a demo here. But if you check out explorer.snarkify.io here now, you can see it live. We don't have a mobile version, unfortunately, right now. If you use your phone, the layout will be corrupted. But this is what it should like. So on the top is all the block proofs we generated for Scroll Mainnet. So we don't claim we generated a lot of proofs that we don't know what it is. This is all the proofs for Scroll Mainnet, and every block is proving a Scroll Mainnet block. So in total, I think right now, if you look at our data, we have proved 100K Scroll blocks, Mainnet blocks over the past 1 to 2 months. And the proving service is elastic, so that if we got more demand from the Scroll side, we can actually spin up more GPUs and to provide more capacity. At the bottom, you can see some proofs are pending and some are already completed. Okay, next slide. So how does this work? I borrowed this slide from Scroll. So if you look at the top, they have the roll-up contract, which is their application contract on their layer 2. Then beneath that, they have the sequencer, which produces the blocks. Like all the transactions are executed and blocks are generated. So then you have the coordinator that generates the proof tasks, like T1, T2 are basically proof tasks for each block. Then you have the coordinator that schedules all those block proofs tasks to those provers. You can see that all those provers, where they call rollers here, are running in parallel so that multiple proof tasks can run in the same pipeline. And finally, all the proofs are generated with an aggregator and updated to layer 1 and get verified. This is the existing Scroll architecture. So we are here to see how can we integrate this architecture with our elastic prover. Next slide, please. Okay. So we create the bottom 3 component in blue is our like software. The top is Scroll Mainnet and Scroll SDK chain. So there are 2 kind of zkEVMs from Scroll. One is their mainnet, that's in production right now. Then is their open source stack called Scroll SDK, where you can launch your own zkEVM with their open source solution. We create a gateway in between so that all the proofs can be routed to the gateway and then dispatched to our elastic provers. Here is a standard problem that we can observe. You can see that the way proofs get approved is different from the mainnet as well as from the SDK chain. So somehow their mainnet is based on a pool model. So if you deploy their prover, you're actually pulling tasks from their coordinator. However, if you are running a Scroll SDK chain, it's actually based on a push model, where the SDK chain will push proof tasks to your infra. This is where there's no standard. Basically, even inside the same ecosystem, they have 2 different ways to generate proofs. We have to abstract that different away so that we can provide a homogeneous proving experience inside our infra. Okay, next slide. Let's look at how our elastic prover work and how it can be integrated with the Scroll infra. So elastic prover provide you the following features. One is a simple proof generation API. It's very simple, just like create proof. However, behind this proof API is elastic and also auto-scaling, so that more jobs you're sending into this create proof generation API, you get more servers spin up and trying to serve those proofs. And finally, it's a pay-as-you-go proof model, because you only pay when you prove something, but you don't pay if you don't. Okay, next slide. This is deck from yesterday. It's not updated. However, I'm supposed to do a live demo here to show you how to deploy Elastic Prover. However, you can try it yourself. If you check out docs.snarkify.io, you will see our documentation online where you can find out a tutorial to launch Elastic Prover on our platform. It has to be in production for a while, 6 months or so. But we recently integrated it with our largest customer to see it in production. But yeah, try it yourself. It's very easy. Just take maybe 3 minutes to finish the workflow, deploy a prover, then you can try generate your proof on your own. Next slide, please. Okay, here's how to integrate with our SDK so that you can use our Elastic Prover service. As you can see, the API is very simple. You just define 3 things. One is a create proof endpoint, which is in the handler. You have a proof function. That's the main thing you want to define. Then you need to define how to serialize your input and your output. Basically, how to serialize your witness data as well as your proof, basically public input, private input, and witness. And then how to serialize your proof output. It's a very simple SDK you can integrate, then you can use our serverless platform. Next slide, please. It's another demo. I want to show you the Scroll Elastic Prover deployed in production, but unfortunately, I cannot do it now. Okay, next slide, please. Okay, here's a main technical stuff. I'll go deep on this one. Let's look at how we optimize our Halo 2 EVM prover for the Scroll circuit. So first, let's look at the target workload. The zkEVM circuit based on Halo 2 were co-developed by Ethereum PSE and the Scroll team. You can see it's a giant circuit. This way to develop zkEVMs is already deprecated, so that the PSE team has already archived this repo, meaning that they are not contributing new code to this repo. Maybe this is still a good example to see how we design zkEVMs and zkEVMs, how the technology evolved. Like this is an old way, like from 2 years ago. Well, 2 years sounds long, but it's quite recent. The traditional way to do this is to manually reaching a giant circuit to describe all the zkEVM functionality. This is not very maintainable. Like once the EVM add a new opcode or a new precompile, you basically have to create a new circuit to describe that new opcode and compile. It's very hard to maintain. Also, the circuit is not modular. You got a giant circuit proof, which creates some problems for our optimization as well. Next slide, please. So this table is more like a tutorial for Planck-proof systems, if you're not familiar with. In a Planck-proof system, you first convert all those circuits in the previous slide into a table. So all the cells in the table is called witness, and all the columns are called instance columns, etc., selectors, but it's not important. But from our GPU optimization perspective, we actually just taking in those giant table and trying to calculate some mathematical relations between those columns, and as well as commit on those columns. Next slide. Okay, here's some parameters of this giant zkEVM circuit. The field is BN254 as on Ethereum, and the row of this table is 2 to the 20. This does not sound large yet. However, once you do the math, it immediately quickly go into a larger called extended domain, which is 2 to the 23 number of rows. This is just the number of rows. If you consider each of the cell, which is a big integer, 254 bits, as you can see, which is 32 byte, which is actually making each column very large. So we are dealing with very large size columns in our GPU acceleration. That could be problematic because we need to move those large columns from the CPU to the GPU, do the computation, and then probably move it back. This is a huge bottleneck there. Then the column count is also very large. For a simple circuit for Poseidon, you probably see under 10 columns, pretty much. However, for the zkEVM circuit, you see more than 1,000 columns, which gives you a huge table. And custom gates and lookups are basically the constraints or relationships between those columns that has to be satisfied. So we need to do those computation over these columns for those custom gates and lookups. Okay, next slide. Okay, here's some performance data. This is a baseline from like CPU baseline. In the whole proof generation process, you have 5 phases. From weighted generation to calculate the lookup arguments, compute column permutation, polynomials, evaluating polynomials, and multi-open. This stuff is familiar with if you are working on ZK proof systems. However, if you're not familiar with them, that's fine. Let's just look at the performance data on the CPU. In total, the end-to-end runtime for this proof generation is 1,700 seconds. Close to 1,800 seconds. You can see it's very long time of proof generation on CPUs. It's quite an overhead. And most of the time, we're spending on phase 3, which is compute the quotient polynomial. And we'll see how we can reduce the compute time with our GPU acceleration. Next slide, please. Okay, the first step to take is, I think, well understood right now, which is optimize the most important compute kernels. It's well known that MSM and entities are taking a lot of time in proof generation. So MSM stands for multi-scalar multiplication. I used to give a separate talk on MSM at ZK Summit, as well as entity acceleration, which is basically FFT over this large field. Those are very compute intensive. With our GPU acceleration, we achieved 3.9 times speed up on MSMs as well as 62 times speed ups on entities, thanks to the open source compute kernels from Zprise. Many of them were did by my co-founder, Niall Emard, as well as the Spark open source library. This is how we improve the baseline of ZK proof computation. Once we open source these high performance kernels, anyone can integrate them in your production system and have faster compute kernels. However, this is only part of the story because, as you can see later, the majority of the compute are not actually on MSM and entities anymore. So we did do more to make it end-to-end faster. Next slide, please. Okay, this is, I think, most technical heavy optimization we did in our end-to-end Halo 2 proving. We built a transpiler to translate Rust computation into CUDA code pretty much. Because here we are doing some polynomial evaluations. We have a large number of polynomials. You can think of, we have many columns, and you need to compute some addition, multiplication, element by element over those columns, and you have an evaluation graph. So how do you compute this thing effectively on the GPUs? Note that you cannot hold all the columns at the same time on the GPUs, so you have to consider how to arrange your data so that you can move some columns, compute the result, save the result, and move some other columns into them, and then merge the result. Think about A plus B multiplied by C, this kind of expression. How do you run it over 3 huge columns on the GPU? So to do this, what we did was, first, we dump the Rust evaluation graph into an intermediate representation. It's a simple IR. Then we write a parser of the IR to translate the IR into CUDA kernels. And finally, we figure out how to arrange the data to run those final evaluation over multiple GPU cards. This is definitely an oversimplification of what we actually did, because this talk is not supposed to be like that technical. Also, this work is done by our another CUDA engineer. So if you are interested in this, how to do this transpiler, reach out and we can follow up with those details. As you can see, the performance is actually very impressive. We reduced, I think, phase 3 runtime from over 1,000 seconds to 36 seconds on the CPU. This is 40 times improvement and account for 61% time reduction on the for the end-to-end runtime. So this is actually the most important optimization we did for the end-to-end acceleration. I think the learning here is that maybe 1 to 2 years before, people think that if you want to build a fast proof generation system, you optimize MSM entities. That's what all people think about. They also think about how to build ASICs for MSM entities. So learning here is MSM and entities are no longer the bottleneck. The bottleneck is on things like this. Then we need to figure out how to build customized algorithms for bottlenecks like this. And once you kick out this bottleneck, some other bottlenecks show up. This is the challenge of doing end-to-end optimization. Next slide, please. Okay, the multi-open is only consumes 1% of the time. I'll probably skip this slide. Let's look at the final end-to-end acceleration result. On the left, that's what I've shown before. You have almost 1,800 second end-to-end runtime. On the right is 3.8 times faster, which is around 469 seconds. Reduced because our optimization of MSM, NTT, as well as polynomial evaluation. However, you can see the blue sector becomes larger, occupies a larger area. That means the weightiness generation is becoming the bottleneck. Weightiness generation is always a challenge for hardware acceleration because it's a scenario, it's kind of a serial computation process where you execute your code you want to prove, and you fill in a table row by row. It's by nature serial. However, there are ways to optimize it. For example, if you look at our latest Z-Price result, which did the end-to-end Planck proof, we actually have a way to do very fast weightiness generation on the GPU for Poseidon-based macrotrees. So we have to look at the weightiness generation process into details to really make this thing faster. This also shows that to achieve fast end-to-end performance, the stuff you want to optimize is very heterogeneous. For example, first of all, we deal with NTT and MSMs. I think people spend 1 year or two that's finally achieved the fast MSM entities on GPUs, and that's solved. Then immediately polynomial evaluation becomes a bottleneck. Then people, I think during the past 1 year or two, this problem is solved again. And finally, the weightiness generation is here. It's not completely solved yet. I think this is work in progress. How can we generate weightiness fast enough on GPUs as well as on ASICs? I think that's an open problem still. Okay, next slide, please. This part is slightly touched by Neil, in the earlier panel discussion, is that it's possible to run multiple provers on the same server to achieve better throughput. It just ensures that there's not a lot of resource competition in your resources. So here, we try to run the same prover, run different number of provers on the same node. It's an 8-card GPU server. So we run 1 prover with 8 GPUs, or 2 provers, each with 4 GPUs, and 4 prover, each with 2 GPUs. You can see the runtimes get higher because they are competing on the CPU side or other shared resources. However, the throughput, proofs per hour, get higher that because like you achieve better resource sharing. For example, if you do one proof 8 cards, when the GPUs are idle, all 8 cards are idle. Them to do some other work instead of making all of the 8 GPU cards idle. So do some resource consolidation can improve the throughput is our learning here, and also confirmed by other teams like zkEVM. Okay, next slide. All right. I think what I've covered is also a simplification of what's actually happening in production. There are more nuances there. For example, in Scroll's proof pipeline, they have the concept called like multiple layer of proofs. What we described is the layer 0, which is actual zkEVM circuit proof generation. After that, they actually have something called layer 1 and layer 2 proofs. These were for proof aggregation. Because if you aggregate the layer 0 proofs directly, it introduces a huge overhead. So to solve that problem, they actually did 2 layers of compression, I can call it, so that the result you get the result Planck table, you get fewer columns and smaller rows, so that it's cheaper to aggregate. Then the layer 3 and layer 4 are actually the batch proof, which is the aggregation layer. So in order to achieve cheap aggregation for batch proof, they actually did 2 more layers of compression on top of layer 0. So that's a nuance in production. It's not just one proof, you have to make it fast end-to-end. You actually have multiple layers of proofs. And then one thing to mention is that we use circuit-specific optimizations because the polynomial evaluation, the transpiler I mentioned, is circuit-specific. Once you change the circuit, we need to rerun that transpiler. So the learning here is it's really good to have a zkEVM circuit, sorry. You have a RISC-V zkEVM so that you have one circuit that you can make it extremely fast instead of have evolving circuit that you have to redo all the optimizations every time. And finally, we figured that data movement between CPU and GPUs are definitely the bottleneck. If we do not solve this, ASICs won't help. No matter how fast the ASIC or your GPU is, if the bottleneck is on data transfer, nothing helps. So the solution we think here is to do zkEVM and GPU acceleration, GPU co-design, or zkEVM ASIC co-design, so that you can reduce the communication between the CPU and the GPUs, or between GPUs, so that you can achieve way better performance. Right now, we are not even saturate the GPUs, and NVIDIA are producing even faster GPUs. So I think we are having software or like zk proof system side problems to saturate the fast accelerators we have. Okay, next slide. Okay, looking into the future. I think I'm tight on time, but I'll touch it briefly. Next slide, please. Next slide. So the first thing is all the zk rollups are shifting to zkEVM based. For example, the Scroll zkEVM, they build on handwritten circuit, but right now they're shifting to zkEVM. Same thing as zkSync side, MATLABs, same thing. I think what's not discussed a lot is zkEVM agnostic rollups. Because all the rollups right now are zkEVM based, actually it does not matter if you prove your rollup with Scroll VM, zkSync VM, RISC-0, SP1, it's the same. You just pick the fastest, lowest cost one. So I think the competition between the zkEVMs are heating up because they are providing like an agnostic interface, which is RISC-V, so that like everything above don't care what kind of VM is underneath. And then one interesting topic is native zk rollups and OP zk rollups. I discussed this with zkSync founder yesterday. Like, what's the overhead of upgrading an OP rollup into zk compared with you running a native zk rollup from zkSync? I think his answer is that OP introduced extra overhead to make it zk. So it has to be zk native to, like the zk rollup has to be designed for zk to make it efficient. The next topic I can discuss maybe is decentralization of proof network. Why decentralization is important for proof network? I think our position is that we are not a decentralization first company. We're not taking decentralization as a first principle. The suppliers can be decentralized so that you can have cheap supply. However, for the infra itself, in the early days, it does not have to be decentralized. You can provide a pretty good service with a centralized proof generation service. And eventually, we will figure out the decentralized payment as well as the decentralized coordination. That's our position. Okay, I think that's all I have. Next slide, please. I have our Twitter and Telegram. So if people are interested, can stay in contact with us. It's just Snarkify_zkP. Very easy to remember. I'm not sure if I have a question next time to take questions, but if you can find it around. Find me around. Yeah, thank you.
Thank you so much, Doctor.
Thank you.
I love calling people doctor.